Number 9 from 5.3 homework. Yeah, let's take a look. Okay, let's take a look. Let's start a new project really fast here. Oops. Well, okay, so it's a good question. So let's have a look. So this matrix number 9, right? It's terrible. So the matrix is the following. It's 3, -1, 1, and 5. So the basic idea here is, how do you tell if it's diagonalizable? You gotta find the eigenvalues first. You can't tell until you find eigenvalues. You're gonna have as many eigenvalues as sort of like the number of rows or columns of the matrix. They're all square matrices. So if it's a 2 by 2, you'll have 2 eigenvalues. Now they might not be distinct eigenvalues, right? You might get the same eigenvalue twice. The important thing here is that when you compute the null space for each matrix like A minus lambda I, or compute the eigenspace, you have to get the same number of linearly independent vectors as the multiplicity of that root. So let's take a look at this problem and just see how it goes. So that's the matrix right there. We want to see if it's diagonalizable. So we have to do the determinant of A minus lambda I, which looks like this. Okay, and if we do that, we get 3 minus lambda times 5 minus lambda minus -1, so plus 1. If we multiply this out, we're going to get lambda squared. We're going to get minus 8 lambda plus 15 plus 1. So that will factor into, so that's lambda squared minus 8 lambda plus 16. So of course that's going to factor into lambda minus 4 squared. So what we have is our eigenvalue. We only have one distinct eigenvalue, but the multiplicity is 2 because of that 2 there. So what we have to do now is compute the null space of A minus, so I call it matrix A, didn't really have a name, A minus 4I. Okay, compute the null space of that matrix. So I'm going to add a new slide here. Okay, so I want to look at that. What is A minus 4I? So it will be -1, -1, and then 1, 1. Okay, and this of course is A minus 4I. So it doesn't take many row operations to just see that this is going to be row equivalent to 1, 1, 0, 0, 0, 0. So again, figuring out the eigenvectors corresponding to this eigenvalue, you have to find the null space. We get x1, so we get, this is a pivot column, this is a non-pivot column. So that means that x2 is a free variable, right? So we get x1 plus x2 equals 0. So we get x1 equals -x2. So that means our solutions look like the following, right? x1, x2, they're going to look like -x2, x2, which is x2 times the vector negative 1, 1. So this vector we got a one-dimensional null space, right? Because if you only have one free variable, that means your null space is going to be one-dimensional. Now if we go back, right, our eigenvalue had multiplicity 2. Remember, to be diagonalizable, I need two linearly independent eigenvalues. Where do we get our eigenvectors? I'm sorry, two linearly independent eigenvectors. Now, there's only one eigenvalue, 4, so they have to come from the eigenspace of 4. But when I try to compute the eigenspace, which is the null space of this matrix, I only get one linearly independent eigenvector. So this matrix is not diagonalizable. If I had two, if I had two free variables in this problem, then it would be, but it's not. Okay? Let me know if that answers your question. So multiplicity of 2 just means there can be at most two linearly independent eigenvectors. In this case, we only had one. Okay, so the multiplicity of that eigenvalue as a root was 2, but we say its geometric multiplicity is 1. So no, you cannot use the same eigenvector twice, right? You have to use linearly independent eigenvectors. Okay, so you have to get two free variables here. We only have one. That means you only get one linearly independent vector here. This vector right here, negative 1, 1. If you take a multiple of this, it won't be independent with that vector, right? So it won't work. Okay. All right, let me try answering Aaliyah's questions here. So 31 and 32 in 5.1. Says in exercises 31 and 32, let A be the matrix of the linear transformation T. Without writing A, find an eigenvalue of A and describe its eigenspace. Okay, so for these problems, it says without writing A. So you could just write A and find its eigenvalues or eigenvectors. But the basic idea here is that if you have these transformations from R2 to R2, they should fix some vectors. So let's just take a look at these. So for section, what is this, 5.3? No, 5.1, sorry. So for 31, it says T is the transformation that reflects points across some line through the origin. So just draw a picture and imagine that it reflects lines across that point. Then think about it. Any vector that lies along that line, let me use a different color. Any vector that lies along that line is going to be fixed, right? But any other, so what does it mean for a vector to be an eigenvector? It means that it stays in its own one-dimensional subspace, right? Because if I multiply by A, it's the same as scaling it by a real number. So what happens is if you have any other vector, like say a vector over here, then it's going to get reflected and look kind of like this, right? Should go like that. So what happens is any other vector that's not along that line is automatically going to be moved into a different, actually that's not entirely true. So there's one other eigenspace. There's one other thing. If you take a vector that is exactly 90 degrees, that's perpendicular with that line, then that will of course be flipped in the opposite direction, which means it's still in its own subspace, right? So there's two eigenvalues for this one. Lambda equal to 1 and lambda equal to negative 1. Okay? The eigenspace of 1 is that fixed line mentioned in the problem. It is the line we're reflecting everything in. Okay? The eigenspace of lambda equals -1 is the line perpendicular, or orthogonal if you wish, to our line of reflection. Okay. Elliot, does that make sense? Well, that's it. So basically, if you have a reflection in that line, anything along that line is exactly the same. It's not, nothing happens to it. Okay, so its eigenvalue is 1. If I multiply by that matrix A, then it's just being multiplied by 1 because nothing happens to it, right? It sends x to itself. Ax is x. But if it's on the line that's perpendicular to the line of reflection, then it's going to be sent to the opposite direction, which means it's still in the same, it still lies along the same one-dimensional subspace, which is a line. So you basically have two eigenvalues, either 1 or -1, because either it's on the line of reflection, which means it stays put, or it's perpendicular, which means it gets sent to its opposite. It gets sent to negative times x. Okay. For 32, T is the transformation on R2 that rotates points about some line through the origin. I'm going to be honest with you, I don't know what that means. What does it mean to rotate about a line? So if you have a rotation can't be, unless this means something I don't understand, rotations can't have eigenvalues. If you think about it, like think about if you have a vector, right? If you have rotation by some angle, if you move it over by, like, say theta radians, by say theta, an angle of theta, it always ends up in a different place unless your angle is pi or 180 degrees. If it was 180 degrees, then it would be lambda equals -1 would be an eigenvalue. I don't know what that means. Rotated about some line through the origin. No, I'm sorry. I actually have no clue what that means. That's an ambiguous statement there. So sorry. So I guess don't worry about it. But if you have a rotation, though, yeah, so rotation that's if it's by pi radians, so 180 degrees, then it would have an eigenvalue, only one eigenvalue, and it would be -1. And it would and basically every vector would be an eigenvector in that case. If you had obviously the angle of rotation was 2 pi, then it would just be the identity matrix, right? 'Cause if you rotate by 2 pi or 360 degrees, nothing changes. So you just have lambda equals 1 as an eigenvalue, and the eigenspace is R2. Like every vector would be an eigenvalue vector. So same thing, if it's rotation by pi or 2 pi, then it would have an eigenvalue of either -1 or 1, and every vector would be an eigenvector. Okay. Other questions? So there's 6 of you in here, so I'm just going to say it because I want to make sure everyone hears it. Do the practice scanning exam that I put on, it's in Canvas, it's on Gradescope as well. Do the practice assignment, get the 4 points. You can get 4 points on your final exam. Do that, please. Okay? There's no reason not to do it. I do not want to have to deal with people that have trouble scanning on the day of the final, because you're only going to have 20 minutes to do it. So you should do a practice run, get those 4 points. Okay? Other questions? Okay. I'm going to put my office hours screen back. Oh, here we go. Yes, so that is exactly true. If you have an eigenvalue that has multiplicity 2, sorry, I have no idea why you got, uh, obviously, apologies here. I have some automatic moderation because obviously, if someone randomly just came in and started using bad language, that would be bad. I don't know why you got timed out here. Um, Apparently, some math words are bad words. I don't understand. An eigen? Maybe eigen? If you say eigen by itself, maybe that counts as a. That's fine. That's funny. Okay. Sorry. Anyway, I got sidetracked here. To answer your question, yes, if it has a multiplicity of 2, but you go through the finding the null space and you only have the one free variable, which means you only have one vector that's linearly independent, then it's automatically not diagonalizable. That is correct. Joshin, if you, yeah, so you can use the fact that 0, 1 is uncountable to show something else is injective. If you just make a or to show someone that other set is uncountable, if you just make an injection from the interval 0, 1 into your set. So if I want to show, say, a set A is uncountable, then if I have an injection from 0, 1 into my set A, then the cardinality of A has to be at least as big as the cardinality of 0, 1. So that would show it's automatically uncountable. Right? So sorry, I was saying do the practice assignment. Do the scanning assignment. There's no reason not to do it. I mean, you can just find a bijection from 0, 1 to 2, 3. It's x plus 2, right? So just take the function x plus 2. That would be a bijection from 0, 1 to 2, 3, and you're done. If you want to show another interval is uncountable, like a different interval, then it's just a matter of um, you know, using a linear function basically. AP equals PD, if you want to do that, that's just to check your work. If I ask you to diagonalize a matrix, all I want that matrix P, which consists of linearly independent eigenvectors of A, and D, which is the diagonal matrix with the eigenvalues along the diagonal. And they should be in the same order, right? So whatever the order the eigenvector's in, their corresponding eigenvalues should be the same order. But if you try to multiply out AP times AP and then try to multiply out P times D, that's just a check. You should get the same thing, right? But you don't have to do it on the test. I don't care. I would say be careful checking because you might screw up. That being said, you can always, I mean, like, I can't stop you from using a calculator, so I've mentioned this in my other lecture earlier. If you're in my my 2 p.m. lecture, then I'll probably say it again. I can't really stop you from using a calculator, but I am going to de-emphasize the scoring of calculations. So for the most part, calculations, I'm going to assume that you're going to get calculations correct. I have no idea, Aaliyah, why you got banned. I gotta, like, it's... okay. Sorry about that. Let me just answer the question, though. If we cannot print the final exam, yeah, then... Yes, that's right. All you have to have is have your name in the same place. Put your ID below it. I don't check the ID in Gradescope because when you import, it doesn't import your ID from Canvas. It imports like a... Canvas assigns you an ID number, so that is, and it's not related to anything, and you wouldn't know it unless you went and like found out somewhere. So uh, yeah, don't you don't need you can put your ID on the page. It's probably very helpful to do that. I mean, like, it really only matters if I have people with the same exact name or people whose names are really close together to have your ID somewhere on the page. But mostly make sure your name is in that box. I just want your name and nothing else for the most part in that box. You can put your ID somewhere lower on the page. But yeah, you don't have to print it out. Yeah, Josh, and because again, if A is uncountable and it's a subset of B, then all you have to do is just make an injection from A to B. That's the identity map, right? Just let f of x be x for every x in A, and have it be a map from A to B. That's an injection. I can go ahead and grade yours, I guess. I don't, I was planning on grading it after everyone submitted, but maybe I'll just do the grades. I can do the grades today. It's due at 9 p.m. When I'm done teaching today, which will be at like 4 o'clock, I'll go and do the grades for those. I'll just check them off. So if you've already done it, I'll have that done. I think I can do that. It should be fine. So that way you can see if you did it right. The problem is I don't know. I don't know if you can publish it first. I'm not really sure, so I can't. I guess you can always email me your name and I'll look it up for you and see how it looks. Yeah, absolutely. Well, so it'll definitely be whenever it gets published. I'll definitely make comments on the grades. I'm gonna go through and like grade them. I'm gonna actually grade them myself, and I'll go through and make comments to make sure that it's right. So if there's something you did wrong, I'll let you know in there. Other questions? Each of the remaining pages. Yeah, put the question number. You don't have to put it on the left. Just put it in the top. Put your name on each page for sure. Yeah, Josh, and unless I ask you to prove it, so if I say prove this theorem, like the proof wasn't in the book and we didn't do it in class, then, you should prove it. But otherwise, if you want to cite a theorem, yeah, you can just say by theorem whatever, or you can say this result was a theorem from chapter whatever. Be explicit. I mean, since you're at home, it's open book theoretically. Yeah, I would just do that. State the theorem that you want to use. Number 19. Sure. Okay, let's see. So it says A is n by n. Suppose A has n real eigenvalues, lambda 1 through lambda n, repeated according to multiplicity. So when it says that, by the way, it just means that you have those n eigenvalues, but some of them might be the same, like lambda 1 and lambda 2 might be identical. Okay. Explain why the determinant A is the product of the n eigenvalues of A. Oh, sure. Yeah, so this is actually probably easier than you think. So for 19, right? We know, so that they're telling you, right, that the determinant, the characteristic polynomial, since the matrix has n eigenvalues, that means its characteristic polynomial is an nth degree polynomial, right? And if it's an nth degree polynomial, we can factor it to look like this. So it's lambda 1 minus lambda 2 minus lambda all the way through lambda n minus lambda. So you have that polynomial, right? Okay. If I want to take the determinant of A, that's the same as just letting lambda be 0, right? So, because don't think of this as being like something weird involving linear algebra. It's just a polynomial. The variable is lambda. So lambda 1, lambda 2, through lambda n, those are just constants. Lambda is the variable. So it's a polynomial, so set lambda equal to 0. Oops. Okay. If you set lambda equal to 0, well, what do you get? On the left-hand side of the equation right here, you just get determinant of A minus 0i, which is just the determinant of A. And on the right-hand side of the equation, you get lambda 1 minus 0 times lambda 2 minus 0 through lambda n minus 0. Well, that's just, you don't have to write minus 0 every time, so you can just write lambda 1 times lambda 2, the product of all the eigenvalues. That's it. So to explain why determinant A is the product of the n eigenvalues, that's exactly the reason. I told you, it was probably easier than you thought it was. Okay, other questions? Joshin, I don't know. I haven't written it yet, honestly. Is it as important as the chapters? Like, do you have to know it? Yes. We did it in class, so you have to know it. If we did something in class, you have to know it. That is my general rule for exams. If it wasn't worth going over, I usually wouldn't cover it. Okay. All right, if no one's going to ask me questions, I'm still here. You can still ask me questions. I'm going to put up the screen just so that I don't feel like a fish in a fishbowl. Sorry, could I briefly explain the ternary expansion? Not really. I mean, think about why we use base 10, right? Why do we have decimal expansions? Because we have, count them. It's hard to get both my hands in the picture here. We have 10 fingers, right? So like when you're counting, you count 0, 1, 2, 3, 4, 5, or sorry, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have to start over, right? Well, imagine you only had 3 fingers. Imagine you only had 3 fingers. You'd say 0, you'd say 1, 1, 2, 3, and then you start over, right? You'd have, I don't know, you'd call it something different. You'd call it 11, 12, 13, and then you'd have, so you'd have different digits, right? So you only represent numbers using those 3 digits now. And so really, I mean, all a decimal expansion is that geometric sum, right? Where you just say, okay, if you have a decimal expansion, that looks like this, A1, A2, A3, and so on, then what that means is that if this is a number, I don't know, call it x, it means that x, well, so if it's a decimal expansion, then all of your digits are in the set of digits from 0 to 9. Okay. So x is a geometric sum that starts at 1, goes to infinity, and it looks like an over 10 to the n. That's what it means, right? Because the 10th place is that digit, you have that digit over 10. The 100th place is that digit over 100, right? So if you think about this, you'd have, if like you had x equals 0.15378 and so on, this would just be 1/10, right? Or let me write this differently. Okay, it would be 0.1 plus 0.05 plus 0.003 plus 0.0007, right? Because it has to add up, right? This is the first decimal place, so it should be in the first. This is in the second decimal place, third decimal place, fourth, and so on. But what are each of these, right? This is just 1/10. This is just 5 over 100, which is 5 over 10 squared. This is 3 over 1,000, so that's just 3 over 10 cubed, and so on. So with the ternary expansion, so this is all decimal. Okay. With ternary, we just don't have 10 fingers, right? So imagine you only had 3 fingers. You just start counting. You add a new digit to you add a new digit to the expansion after every 3 instead of after every 10, right? So, or after every 9, I guess. Well, 10. So for ternary now, okay, you have x equals where again your an is in just the digits 1, 2, 0, 1, or 2. And so again, now x equals a geometric sum, n goes from 1 to infinity, of an over 3 to the n. So in a ternary expansion, if you had it, right, if x was equal to, say, 0.12021, okay, this would be, again, 0.1 plus 0.02 plus 0.000 plus 0.0000, no, sorry. That 0 there threw me off. 2, and so on, right? But in this case, they represent different things. This is not a decimal expansion like you normally think. It's that digit over a power of 3, right? So this is now the 3rd place, the 9th place, the 27th place. So it would look like, 1/3 plus 2 over 3 squared plus 0 over 3 cubed plus 2 over 3 to the 4th, and so on. I don't really know any better way to put that, right? Anyway, that's it for Amsterdam. So Joshin, you can ask me more questions at 3 o'clock when I do lecture for Math 13, okay? But in any case, guys, I'm going to sign off now. So feel free, if you're a Math 3A student, come by the lecture in in 10 minutes, and then I'll have my Math 13 lecture at 3 for Josh, and I think he's the only one here in Math 13. So anyway, that's it. All right, I'll see you guys in a few minutes. I'm gonna take a little break.